it. Try it. If I took a family of curves, this is easy to demonstrate in Desmos. So if we go to the graphing utility here, like I could take, for example, I could take a family of curves of the form y equals mx plus b, right? And if I start off with m equals 1 and b equals 0, that's a pretty basic line, right? But by tweaking those parameters, I'm going to create a whole bunch of different functions that look very similar. They have the same characteristics, right? But they're going to be slightly different. Does that make sense? Okay? So that's all we're talking about when we say families of curves. They all have the basic same look to them, but they're going to be, they share the same characteristics, but they're going to be slightly different based on the values of the parameters that we apply to those, to the curves. Okay, in order for us to really, and we do a lot of work with families of curves, like when you get into calculus and eventually you get beyond calculus into differential equations classes, a lot of what you do is you work with, you know, orthogonal families of curves and things like that. So where you're trying to find families of curves that are mutually orthogonal, so they're always going to intersect at right angles, for example, right? And eventually, in a couple of years, we'll talk about that a little bit. Okay, but for now, we're just kind of introducing some of the brief vocabulary. In order to understand that, though, we always want to understand families of curves based on the simplest possible representation, which we call the parent graph or the parent function. So in the linear one, we're not even going to really mess with that. The parent, we'll use it as an example, but then I'm not even going to. It's not even on the Moodle assignment that goes with it. You guys are already so, you know, lines are so easy for you. It's not a big deal. But all the other ones, we're going to focus on a little more, with a little more detail. So if we wanted to write the most basic parent function for a line, you know, what is it? Y equals y equals x, right? That's it. Okay, so what's the domain of the, and if we graph it, all it looks like is just the line, right, with the slope of 1 through the origin, okay? What's the domain?
All real numbers.
All real numbers, okay? What's the range?
All numbers.
Okay, what's the x-intercept? Okay, good. It's going to be the point 0, 0. What's the y-intercept? 0, 0. Good. What's the maximum? Now we got to make sure we understand what this means. The maximum number of roots or zeros. So what's a zero of a function?
Origin.
A real. Okay, so a zero is where the function, meaning the y value, equals 0. Okay. So if it's a real 0, that means that it's going to be an x-intercept. We're going to look at some examples when we get into quadratic functions here very soon. We're going to look at some examples where we could have some roots and zeros that are not real, right? But they're still zeros of the function. It's where the function equals 0. But it's always, all of the zeros of a function could be real zeros, right? And if they're real zeros, they always correspond to x-intercepts. But what's the maximum number of x-intercepts that we could possibly get from a linear function? 1. Okay, right? That's it. You can only give one solution to a linear equation. End behavior. Now, this is the part I want to really focus on the vocabulary here. In calculus, we're going to call end behavior. We're going to deal with end behavior by talking about limits. Okay, and that's a, you know, that we won't really use that terminology. I'm going to introduce it to you now because it's just good to be thinking about it. But we're not going to do a lot with limits until you get into calculus, and that's our first big topic in calculus, is we learn how to do a bunch of interesting things, but by taking what we call limits. What limits are going to do for us now, they do more than this, but for now, the limits we're going to use to describe the end behavior of a function. So what do we mean by end behavior? End behavior deals with the behavior of the function way out there and way out there. So we're talking about at the kind of the ends of the function. Well, it doesn't really have ends. If the domain is all real numbers, the function's going to go forever in the positive x direction and forever in the negative x direction. But we want to know what's the behavior as we get way out there, right? In other words, as x approaches infinity or as x approaches negative infinity, what's the behavior of the function, okay? So we can say that in a couple ways. Like in calculus, we'll say it this way. We'll say something like this, like if we have the function f of x equals x, there's our linear parent graph, right? We'll say something like this. We'll say the limit, we'll write that as just LIM. The limit of the function as x approaches infinity is some answer, right? And by that, what we mean is, how could you describe the behavior if we move infinitely far in the positive x direction along this function? What is the function, meaning the y value, doing? So as x approaches infinity, what's y doing? It's going up forever. It's approaching infinity, isn't it? Right? So the answer here would be, as x approaches positive infinity, f of x approaches positive infinity. And we would write this a couple years in calculus. We'll just write it like that. The limit as x approaches infinity, the limit of f of x as x approaches infinity is infinity. And that tells us, it doesn't tell us exactly what's going on, but it tells us the trend. When we go, if an ant were to walk along this function infinitely far horizontally to the right, he's going to walk up infinitely far also to get there, right? So you tell me then, as x approaches negative infinity, what is the function approaching? Negative infinity. Okay, you get the idea?
So it would be continuous.
And this was one that would be continuous, exactly. So we would circle, this is going to be continuous, isn't it? Okay, now you guys, now just, you don't need to write anything down in your notes here unless you're using pencil and you can erase it. But I want you to just take a second and see if you can remember what an absolute value graph looks like. And see if you can just take at least an educated guess at what all those answers are going to be. Just take 30 seconds or so and see what you get for that. Let's use function notation, just so we do it the same way all the way through. Being as we're talking about parent functions, I'm going to make one small tweak. I'm just going to rewrite that using f of x instead of y. It doesn't really change anything.
You want us to do that too?
I would.
Okay.
I would. So now, what do you know? Absolute value function, what is the parent function of an absolute value function? F of x equals absolute value of x, the simplest possible absolute value function we can make. Now, the most important thing is the graph, right? And the graph, doing the graph first helps us answer all the rest of these questions. So what's the shape of an absolute value function?
A U.
No,
It's
it's
Oh,
it's
this,
a V.
oh yeah,
it's
it's
a
a
V.
simple pattern.
Wait, I'm
Right, so
right.
the vertex is going to be, now in math, what's a vertex mean? Like in geometry, you guys talked about vertices, right? Singular is vertex, plural is vertices. Those were the corners of polygons, for example, right? So when we're talking about, and this isn't geometry, when we're talking about analysis, right, where we're looking at, algebra analysis, where we're looking at graphs of functions, a vertex is going to be kind of the point of the function, right? So in this case, it's pretty obvious. It's going to be the point of the V. And that's what an absolute value function looks like, right? So the coordinates of the vertex, I'm going to write these in. Coordinate of the vertex are 0, 0, right? It's on the origin. And we want to maybe put a couple other guide points in. I didn't draw that right side very well. I'm going to redraw that. I got to be a little more careful with my drawings. So a couple guide points. So we know that an absolute value function, the parent function, is going to go through the point 1, 1 and the point negative 1, 1 also. So in other words, it's going to rise by 1 and run by 1. It's going to rise by negative 1 and run by 1 on the other side. The slope of the right-hand leg is going to be 1 and the left-hand leg is going to be negative 1, right? So let's just add those points to our picture. Okay, and there's our parent graph, right? It's a V, slopes of 1 and negative 1. What's the domain? All reals. Okay, now what about the range? What's the range? Cahill, what's the range going to be of this graph? What about what's y going to be? Greater than or equal to 0. Okay, so there's our range. What's the x-intercept going to be? What's the y-intercept going to be? okay? What's the maximum number of roots or zeros of this function? Okay, now this one is gonna be 2. It's gonna be 2 because, now you wanna be thinking ahead here on this. What we're gonna do with this parent graph is our goal is, once we get to a point where we're starting to work on transformations of these parent graphs, we're gonna tweak the parent graph to create other absolute value graphs, right? Like, for example, we'll be able to reflect this thing vertically, so the V opens down. We'll be able to slide it around in the plane, so the vertex moves from, it would be at other places other than the origin. We'll be able to stretch it vertically, which means compress it horizontally, or we'll be able to compress it vertically, which corresponds to stretching it horizontally. We'll be able to do all these things to it, right? To change it'll share the same characteristics, but it'll look different, right? So when we do all that stuff, what's the maximum number of x-intercepts that we could get? Well, we could get 3 if I slid this thing, or could get, sorry, 2, not 3. If I slid this thing down a little bit, I could get 2. Okay, that's gonna make more sense a little bit later. But for now,
So it doesn't have to be 0, 0, 0?
well, the parent graph does, but later on, when we start to do transformations of this thing, what if I translated it down a little bit so the vertex was down here somewhere? Then the V would open up and I'd end up with 2 x-intercepts, right?
So it can make that.
So when we talk about the maximum number of roots or zeros, we're talking about after we transform the function later on. I mean, what's the maximum number of solutions we could get from an absolute value equation? Well, think back to our experience solving absolute value equations. How many solutions did we typically get? 2, right? 1 for the plus and 1 for the minus. Occasionally we got 1 if you know, and that would correspond to the 0 being at the vertex, and sometimes we actually got none if there were no real solutions, right? That happened a couple times too. Graphically, as we'll see, that would be the situation where if I took this thing and I translated it up so the vertex was above the x-axis, so there were no x-intercepts, right? But the maximum number I could get is 2. Okay? Now fill in these blanks. As x approaches infinity, Trey, what does y approach? F of x approaches what? As x approaches infinity. Infinity. Good. As x approaches negative infinity, f of x approaches infinity, positive infinity, doesn't it? Everybody see that?
Yeah, also.
Okay, because as we go to the left forever, we also go up forever, right? We're talking about the parent graph. Is this one that's continuous or discontinuous? Continuous. I can draw this thing without ever taking my pen off the board, right? Okay. All right. What about quadratic? You've had some experience with this. What's a quadratic function look like? Good. F of x equals x squared. Okay, so what are the characteristics of the, let's draw the parent graph. It's going to be a parabola, right? So this is the one that's not U-shaped, it's kind of a V-shape, right? Or I mean, it's not V-shaped, it's kind of a U-shape, got it backwards, right? Absolute values are V's, quadratics are parabolas, so they're kind of U-shaped. Well, where's the vertex, sort of the point of the U? The origin, so it's right here. And then if I go 1 to the right, how far up would I go?
1.
I'd go up 1. If I go 2 to the right, how far up would I go?
4.
4, good. Okay. If I go 3 to the right, I'd go up 9, and so on. And then, we're not talking about this today, but this is a function like the absolute value function that has symmetry, right? I could fold this thing over the y-axis, and I would create the imprints of the corresponding points on the other side of the graph, right? And so, that's my picture I get. Okay, did we get that? Okay, what's the domain of this function?
The domain is all real numbers.
All real numbers, good. What's the range? Greater than or equal to 0. X-intercept is getting boring, 0, 0. Y-intercept is 0, 0. What's the maximum number of roots or zeros? So if I were to solve a quadratic equation, what's the maximum number of solutions I could get? 2. Those correspond to when I transform this thing, I could create a graph of a quadratic function that has two x-intercepts, so two real solutions, right? We can see that in terms of the graph, okay? As x approaches infinity, y approaches, or f of x approaches infinity. Well, okay, but just I mean, you're right, it's gonna get to infinity faster, but it's still just approaching infinity, okay? It's going up forever. As x approaches negative infinity, f of x approaches infinity, good, okay? It is clearly continuous, right? Okay, questions? So far, so good? Okay, f of x equals what for a cubic function? X u. Okay, good. Okay, so now a cubic function, if we make the parent graph, this one looks a little different, right? This one, in fact, I'm going to throw something else at you guys here. It's kind of, we'll come back to this later, but I think it's important to at least see it in terms of the parent graphs here. I wanted to find, so you have to write these notes down because they're not, it's not a handout.
Oh, so we're not doing that?
Yeah, write this one down. So I want to give you two different flavors of symmetry that are really important in math. We can talk about lots of different kinds. When I say flavor, I mean just types of symmetry.
Hope you write them on
Okay,
this.
so there are two main types of symmetry that we talk about that would be relevant to what we do in algebra. It's odd symmetry and even symmetry. I want to define those for you, and I want you to see what they mean in terms of a graph. But I don't want you to think that this is it. There are all kinds of symmetry that we talk about in math and physics. Like we just talked about in calculus the other day, time symmetry. And you can talk about time symmetry in terms of physics, some of the physics we talk about in calculus. And it means something just as interesting. I'm here just in a nutshell, this is what time symmetry means. If I were to throw a ball up in the air, right, the ball is going to start going pretty fast, and because of gravity, it's going to slow down, it's going to decelerate until it gets to the apex, and it's going to just change its direction. So it's going to have a velocity of 0 for just a moment, instant in time. And then it's going to fall back down in my hand, right? Now, if I film this with a video camera, could you tell the difference if I were going to use some kind of editing software and I filmed the ball going up into the air and then I just reversed the video so you saw just the reverse of the ball going up? Could you tell the difference between that and me filming the entire path of the ball where it goes up and comes down?
Yeah.
You could?
Well,
I
is
don't
it the
think-
same speed?
I don't think the film's at the same speed. I don't think you could, right?
Well, what if? It doesn't. I mean,
You see what I'm saying? You couldn't tell any difference because they're mirror images, right? The ball's going to start off going pretty fast and it's going to slow down when it gets to the apex. On its way down, it's going to start slow and it's going to speed up until you catch it in your hand. And if we ignore the effects of air resistance, which aren't very significant if you're just throwing a ball in the air, you'd find that the speed it leaves your hand is the exact same as the speed at which you catch the ball, right? And so you couldn't tell the difference. The two would look indistinguishable. The reverse of the upward journey would be exactly the same as the downward journey. That's time symmetry, right? It doesn't make any difference. Going forward or backward in time there is indistinguishable, right? And so you see that a lot in physics. And so this idea that we talk about here in Algebra 2, I mean, you can take this a lot further later on with different types of symmetry. There are some really bizarre symmetries. Like you look in, we talk about string theory, where you have 11 spaces. Actually, in string theory, it's actually split up into 3 extended dimensions that we know about, x, y, and z. But then there is an additional 7 tightly curled up dimensions that are on a really small scale that we don't really see, but they manifest in like some ways that the universe works. And it actually, string theory describes the universe really well. But there are some weird types of symmetries in string theory. When you include time, you get this 11-dimensional space. And there are these 7-dimensional little geometric entities called Calabi-Yau spaces. They're really complicated, they're 7-dimensional, but these things have some weird types of symmetry that are just much, much more complicated to understand than this, but it's the same, it's just an extension of the same kinds of thinking that we're doing now, right? So this is just, I mean, it's just the first step towards a long discussion of symmetry that you'll have in math as you move through classes. You'll always talk about new and different types of symmetry that are just increasingly, hard to, they're not obvious. Like these two you'll find to be pretty obvious. So even symmetry, in math is described this way. If f of negative x equals f of x, that's the test we do for even symmetry, okay? What it means is, when you have even symmetry, it means you have reflective symmetry or line symmetry about the y-axis, okay? So let's look at an example. If we go back to our graphs, would you agree that this quadratic function has line symmetry about the y-axis? If I fold it over the y-axis, it overlaps. Agreed. And so does the absolute value function, right? Okay, so the test is then, for that type of symmetry would be, if we take that function and we plug in a negative x, if I'm going to get back to the original function, f of x. Let's try it. Let's try it for f of x equals x squared. And don't panic, I'm not gonna probably put this on the test or anything. I just want you guys to see this, it's really interesting, it's really cool. We'll get to this eventually where this will be a bigger deal. So if I try f of negative x, remember what our rule is, right? When we're substituting into a function, what do? We take the x and we replace it with an empty quantity to dump the substitution into. And this time, we're substituting in a negative x, right? But what is negative x quantity squared? Negative x times negative x is just x squared, isn't it? Right? So this is giving us back x squared, which is f of x, right? So when we evaluated it at negative x, we got back f of positive x, right? And so that, it passes the test for even symmetry. So we know this is going to have folding symmetry about the y-axis, right? Okay, let's try that for an absolute value function. Okay, so for an absolute value function, if we say f of x equals the absolute value of x, let's evaluate this at negative x. We're going to get what? If f of x is the absolute value of x, what's f of negative x?
The absolute value of negative x.
The absolute value of negative x. Well, what's the absolute value of negative x? It's x. Yeah. Well, I won't say that. I'll say it's the absolute value of x for reasons, and I'll prove it to you. There's a little property here we can use. The absolute value of a times b, we could write as the absolute value of a times the absolute value of b. That's true. Okay. So the absolute value of negative x, I could write as the absolute value of negative 1 times the absolute value of x. What's the absolute value of negative 1? 1, right? So that makes it the absolute value of x, which is f of x. So look what we got. F of negative x gave us back f of x. So it also passes the test for even symmetry, and so it should have line symmetry or folding symmetry about the y-axis, which it does, right? Okay? Questions? Okay, I mean, you see what I'm saying when I talk about even symmetry then. Okay, so what about, let's look at a different kind. Let's look at if even symmetry is one kind of symmetry, what do you think the other type of symmetry I'm going to talk about is contrasted? Odd symmetry. Right, so odd symmetry looks like this. So odd symmetry, the test is f of negative x equals negative f of x. Okay? Do we have, and what it manifests as in terms of like graphical symmetry, it's going to be rotational symmetry about the origin. And we'll talk a lot more about this when we talk about polynomials, and that's really where the names come from. Our even and odd comes from the way these symmetries work with polynomials. So we'll revisit this again later in the year, and it'll make a little more sense probably. But think about what's rotational symmetry. Now go back to geometry, right? When in geometry you would have said, let's do just a quick review of some of these topics. So like in geometry, give me an example of a shape that has line symmetry. A rectangle. Okay, rectangle would. So if I draw a rectangle, what's that color?
I like that.
So if I draw a rectangle, it's got line symmetry because I can fold it along I can make a certain fold where it'll overlap completely, right? Like everybody see what I'm saying? I can fold it right here. And it'll overlap, okay? Is there another line I could use to fold it?
Yes.
Okay, I could also go this way, couldn't I? Okay? Give me an example of a shape that has rotational symmetry. Okay, a circle has lots of rotational symmetry. It has infinite rotational symmetry. Right? This has like 2 degrees of folding symmetry. Circle has an infinite number of degrees. Can somebody give me an example of a shape that has 3 degrees of rotational symmetry? Triangle, so an equilateral triangle, okay. So if I were to do that, right, I could take, and what that means is, if I were to put a tack in the middle of that piece of cardboard and spin it around, I could spin it so this vertex ends up there, right? And I could spin it again so that vertex ends up there, and I could spin it once again so it makes a complete rotation, right? Okay, does that make sense? And so anytime I can spin a shape and it overlaps with itself, we say it's got some kind of rotational symmetry, right? Yes, sir?
Does that mean the rectangle has rotational symmetry?
The rectangle does not have rotational symmetry.
Not if you rotated it like
180.
180 degrees?
Oh, okay, sorry, yeah, you could, I guess you could rotate it from there to there, yeah, you could, you're right. It does have rotational
But it
symmetry.
only
One
has
little
two.
bit, yeah, you're right. When we talk about rotational symmetry here, we're talking about rotational symmetry with a 180 degree spin only, right? So we're only talking about if we spin this thing 180 degrees around the origin, okay? Do any of these shapes that we've looked at have that type of symmetry, where they would
The first
overlap
one
completely
does.
if I spin them 180 degrees?
Linear.
Linear does, doesn't it? Right? If I put a tack right here, I could spin that thing half a spin and it would overlap, wouldn't it? Okay, so let's do the test on it. Let's do our test for odd symmetry. This is a pretty boring function to use, but we'll use it. So if f of x equals x, what's f of negative x equal to?
Negative x.
Negative x, right? Well, what is that? That's equal to negative f of x, isn't it?
Yeah.
So f of negative x is equal to negative f of x, and so we know that that one, guaranteed, that one has rotational symmetry, it has odd symmetry. Okay? All right, so now the reason I bring this up, let's go one step further here to our cubic function. Okay, our cubic function, let's test this one before we graph it to see if it has any symmetry, okay? So if we go back and we apply our test, let's do it down here. We don't know what the outcome's gonna be maybe yet, right? So if we try for our cubic function, f of negative x, what's f of negative x gonna give us back? Well, every place I have an x, I'm gonna replace that with a quantity to dump the negative x into. So would you agree I've got the quantity negative x cubed, right? So negative x times negative x times negative x. What's the outcome of that?
Negative x.
Okay, the quantity negative x cubed is negative x cubed. Okay, but f of x is x cubed. So isn't that the same thing as negative f of x?
Yeah.
So what kind of symmetry does it have?
Rotation.
It's got odd symmetry. It's got rotational symmetry about the origin, guaranteed, right? So what's nice about this, and this is the argument, or this is the real value of symmetry a lot of times in math, is you can avoid doing a lot of work. Like in calculus, when we're doing our curve sketching in calculus, which we're moving up to, if people can find that we have certain types of symmetry, man, it cuts down the calculus by a factor of 2, because you could just graph half of it, and then you know what the other half looks like.
So it's like
right?
that?
Okay, right, so now let's make a little t-table, and let's figure out what the right half looks like. If I evaluate this function at 0, what am I gonna get for my y value? 0. Okay, so we know we got the point 0, 0 that it goes through. If I evaluate it at 1, I get an output of 1. So it goes through the point 1, 1. If I evaluate it at 2, I get an output of 8. Okay, so I gotta go over 2 and up 1, 2, 3, 4, 5, 6, 7, 8. So I'm clear up there, right? And so this thing's gonna look like, kinda like that, right? On the right side. Well, what's it gonna do on the left side then?
It's gonna do the.
The exact opposite is when it goes down.
Right, it's gonna do that. That's a pretty bad picture, but you get the idea, right?
That's nifty.
Okay?
Why did I say nifty? That's
So what's the domain of this function?
The domain.
reals,
All reals? What's the range?
all reals.
What's the x-intercept?
The x-intercept is 0, 0.
And so is the one.
And the y-intercept is also 0, 0. Okay, the maximum number of roots. Now this is stuff that's gonna be a little bit weird right now. But if I were to come up with a cubic equation, we haven't even done quadratic equations yet, but you guys remember quadratic equations well enough to know that a lot of times when you solve a quadratic equation, you're getting 2 answers back, right? Okay. What about a cubic equation? What's the maximum number of answers you could get back in a cubic equation? Their answer is 3. Okay, I'm gonna prove it to you. You remember one of the ways we can think about this. This is our parent graph, correct? Okay, so that's a parent graph. Can I create a cubic equation that has a more complicated cubic equation, which has the same characteristics, but looks much, much different? And the answer is, yeah, I can do that. I can do that. Like, for example, if I were to, I could take a cubic equation like this. Give you an example. So here's a cubic equation. If I did y equals, let's see, I want to do like x cubed minus 2x squared
Whoa, that's good.
plus 1. There's a cubic equation, right? So it does some weird things to it, right? But it's still got a lot of the same characteristics, but how many x-intercepts does this one have?
3.
1, 2, 3. Okay. So we could get 3 x-intercepts in a cubic equation too. Okay? If we tweak it enough, we could get 3. So what's going to be the end behavior of our parent graph? As x approaches infinity,
Y approaches
y approaches infinity. As x approaches
negative.
Negative infinity.
negative infinity, and it's continuous, right?
Yeah.
Okay, good.
Yeah.
If we're not going to do a quartic, which would be a f of x equals x to the 4th, but what kind of symmetry do you think it would have?
I guess.
What do you think it would be?
The second.
Even?
Oh, it's the one
It'd
where
be-
it's like this and then
It'd be, a quartic would be even also. Now, can you make a guess at what do you think those evens and odds might be about? You can start to a little bit. It's the exponent of a power function, isn't it, right? If it's an even exponent, it's going to have even symmetry. Doesn't that make sense? Because I'm going to be taking negative x to an even power, which is going to make the answer positive, isn't it? Right? All the negatives will cancel. If I have a power function where x is taken to an odd power, you're going to get odd symmetry. Like y equals x is the same as y equals x to the 1, isn't it? Right? Okay, question. Okay, so we can do it 2 ways. Let's show that. So negative x cubed is the same thing as negative x times negative x times negative x is one way to look at it. What's negative x times negative x?
X.
Positive x squared, right? So positive x squared times negative x, negative times positive is negative, and x times x squared is x cubed.
I got that. How does it equal this?
How does f of negative x equal negative x cubed? Because that's just our rule, right? Look, think what we do with the function. The rule is whatever I'm inputting, I'm cubing, right? So if I'm inputting a negative x, then I have to cube the negative x. Okay? All right. Good place to stop. Well, this is taking a little more time, but I really think it's a good discussion, so we'll continue this tomorrow. We'll talk about some different kinds of functions tomorrow, for paragraphs.